Hello everyone. This video is part of the course Introduction to Biostatistics or Statistics in general. Today we are going to look at the basic concepts related to statistical inference. Statistical inference is a method of drawing valid conclusions about the characteristics of a population based on the results obtained from a sample. And there are two important terms that are essential for statistical inference. These are population parameter and sample statistic. Population parameter is a fixed, usually unknown summary measure of the characteristics of a population. For example, population mean, which is usually denoted by mu, population variance, which is usually denoted by sigma square, population standard deviation denoted by sigma, and population proportion denoted by pi are the most common population parameters or summary measures of the population. And on the other hand, we have statistic, which is a known summary measure of the characteristic of a sample. So sample mean, which is usually denoted by x bar, sample variance denoted by s square, sample standard deviation denoted by s, and sample proportion p are summary measures of the sample, or they are called sample statistics. So the population parameters are usually assumed to be unknown, whereas the sample statistics are usually known because they are going to be calculated from the sample. So statistical inference, in other words, is making conclusions for population parameters using sample statistics. Here we have identified the sum of the parameters and some of the corresponding statistics. Therefore, drawing valid conclusions about these population parameters based on these sample statistics is called statistical inference. So there are two forms of inference. One, it is called parameter estimation, and the other, test of a hypothesis. So in the case of parameter estimation, it's just determining a specific value for a population parameter of interest. So for example, if we say, what is the proportion of smokers among lung cancer patients? Now here we are intended to find a certain specific value for the proportion of smokers. So here the aim is estimation. What is the mean systolic blood pressure of patients under antihypertensive treatment? And again here, we are interested in finding a certain specific value for the population mean systolic blood pressure of patients. On the other hand, when considered as of hypothesis testing, it is testing whether a particular value for a population parameter is plausible or not. So the question is the proportion of smokers among lung cancer patients 0.72. Now here the parameter of interest is the population proportion of smokers. And here we are intended to determine whether 0.72 is a plausible value for the population proportion of smokers. Similarly, if we say, is the mean systolic blood pressure of patients under antihypertensive treatment 120? So here the population parameter of interest is the population mean systolic blood pressure, and we are interested in testing whether 120 is a plausible value for the population mean systolic blood pressure of patients. So in the case of estimation, we need to estimate the value of the population parameters within a certain specific value. In the case of hypothesis testing, we have a certain assumed value, and we are interested in checking whether that value is plausible or not for the population parameter of interest. Now let's denote theta as a certain general population parameter, and let theta hat be the corresponding statistic. Then the statistic theta hat intended for estimating the parameter theta is called an estimator of theta. So the formula that is used to estimate the population parameter of estimate is said to be an estimator. And a specific numerical value that's going to be obtained from the estimator is said to be an estimate. So an estimate is a certain specific numerical value obtained using that of the estimator or the formula. So estimation is, in general, obtaining an estimate of the unknown value of a parameter by a statistic. We need to estimate the value of the population parameter using a certain sample statistic. And here there are two types of estimations. One it is called point estimation, and the other it is called interval estimation. In the point estimation, we are interested in finding a single sample value for the population parameter of interest. So for example, sample mean is a population estimate, that's of a point estimator of the population mean. So the formula 1 over n times sum of xi, I runs from 1 up to n, is said to be an estimator. And a single sample value obtained from this formula is said to be an estimate. So here x bar is a point estimator for mu, because using this formula we are going to obtain a single value. So that single value is said to be point estimate of mu, and this formula is said to be a point estimator of mu. On the other hand, if we are interested on the population proportion pi, so the estimator, let's say sample proportion p, which equals 1 over n times sum of xi, here where xi is a binary variable taking values, let's say 0 and 1. So here p, or sample proportion of, let's say, success or sample proportion of ones, is a point estimator of pi. So the formula is a point estimator, but a single sample value that we are going to obtain for p is said to be a point estimate of pi. So the formulas are estimators, but their corresponding single sample values obtained using these formulas is said to be point estimates. So let's consider some examples of point estimates. If we say the proportion of smokers among lung cancer patients is estimated to be 0.72, now here the population parameter is proportion of smokers among lung cancer patients in general. So if it is estimated to be 0.72, therefore 0.72 is a point estimate for the population proportion of smokers. So we can say P equals 0.72 estimates pi, or 0.72 is a point estimate of pi. And the formula used to obtain this 0.72 is an estimator for pi. Similarly, if we say the mean systolic blood pressure of a sample of patients under antihypertensive treatment is 120 millimeter mercury, now in this case, the mean systolic blood pressure of a sample of patients. Therefore, here a sample of patients indicates that it is a sample statistic. Therefore, 120 is the sample mean that is used to estimate the population mean systolic blood pressure of patients in general. So x bar 120 millimeter mercury estimates mu. So 120 is a point estimate of the population mean mu. And this population mean is nothing but population mean systolic blood pressure of all patients under antihypertensive treatment. So the formula used to obtain this 120 millimeter mercury is an estimator for mu, but this single sample value 120 is a point estimate of mu. So point estimates or point estimation in general is a method of obtaining a single sample value used to estimate the population parameter of interest. But a point estimator has some disadvantages. One, it doesn't indicate the extent of the possible error, because we don't know how close the point estimate is to the true value of the population parameter. And the other, point estimates cannot attach any degree of confidence. We cannot be certain how close the values are to the actual value of the population parameter. Because of these limitations, there is an alternative way of estimation called interval estimation. And this is considered to be desirable because it is the determination of an interval or a range of plausible values on both sides of a point estimate within which a population parameter is assumed to lie within a certain degrees of confidence. So in an interval estimate of a population parameter, it is of the form like we will have a lower bound and an upper bound, so that we have an infinite, let's say theoretically, we will have an infinite number of possible values for the population parameter of interest. So if we go back to the previous slide, now here 0.72 is the sample proportion of smokers, but how much this value is close to the actual value of pi is unknown. Similarly, the sample mean 120 is a point estimate for the population mean mu, but how much this 120 is close to the population mean is unknown. Therefore, instead of the point estimates, it's better to consider that of an interval estimate, and the process is called interval estimation, just finding a certain range of values for which our assumed parameter of interest is going to lie. So now let's consider examples of interval estimates. Considering the previous examples, if we say the proportion of smokers among lung cancer patients is between 0.67 and 0.77, now here the population parameter of interest is population proportion of smokers among lung cancer patients as a whole. So if we say this proportion is in between 0.67 and 0.77, therefore this range values from 0.67 to 0.77 is an interval estimate for the population proportion of smokers. That means our population parameter of interest lies in between these values. So at least here we have some range of values between these two extremes. And again, using the previous example, if we say the mean systolic blood pressure of patients under antihypertensive treatment is between 110 and 130 millimeter mercury, in this case again, the population parameter of interest is the population mean systolic blood pressure of patients. And here we have the interval that this population parameter lies between 110 and 130. So here the range from 110 to 130 is said to be an interval estimate for the population mean systolic blood pressure. Therefore, a point estimate is finding a single sample value, but an interval estimate is finding a certain range of values for which the assumed population parameter of interest lies. Now let's consider that of the second concept related to that of statistical inference. The first is estimation and the second is hypothesis testing. So now let's consider the concept which is called statistical hypothesis. A statistical hypothesis is an assumption or a conjecture about a population parameter of interest. So we may have certain population parameter of interest, and we may have certain assumption about that population parameter, and the assumption may originate from a certain observed behavior, natural phenomena, or from a certain established theory. So for example, if we have, let's say, a question of interest, something like, is the proportion of smokers among lung cancer patients 0.72? Now here, the population parameter of interest is proportion of smokers among lung cancer patients. And here we have an assumption that it is 0.72. Now 0.72 is not a sample value. It's just an assumption that's obtained from a certain, let's say, our observation or a certain established theory or from a certain natural phenomena. So here we are interested in testing whether the population proportion of smokers is not significantly different from 72% or not. We need to check whether 0.72 is a plausible value for the population proportion of smokers. Similarly, if we have the question, is the mean systolic blood pressure of patients under antihypertensive treatment 120? Now here, 120 is not a sample value. Rather, it's just an assumed value or hypothesized value for the population mean systolic blood pressure of patients under antihypertensive treatment. So here our question of interest is to check whether 120 is a plausible value for the population mean systolic blood pressure of patients under antihypertensive treatment. So a statistical hypothesis, an assumption like this, assuming 0.72 for the population proportion and assuming 120 for the population mean. So it's just an assumption or a conjecture about a particular population parameter. So such an assumption originates from speculation concerning a certain observed behavior, natural phenomena, or a certain established theory. So hypothesis testing is a statistical procedure that leads to a decision about a statistical hypothesis concerning a population, concerning a population by examining a sample from that population. So if we have these assumptions like whether the population proportion is 72% and the mean systolic blood pressure is 120, for this we are interested in making a decision about this hypothesis concerning the population by examining a certain sample from that respective population. So there are two mutually exclusive and exhaustive hypotheses about the parameters in question. One of the hypotheses is said to be null hypothesis, which is usually denoted by H naught. Now, this null hypothesis states there is no difference between a population parameter and hypothesized value. On the other hand, the alternative hypothesis is denoted by H1 and states that there is a difference between the population parameter of interest and the hypothesized value. Therefore, these two hypotheses H0 and H1 are mutually exclusive. Here in H0, we say there is no difference between the population parameter of interest and the hypothesized value, but in the alternative, we are going to say there is a difference. So they are mutually exclusive. In addition, these two hypotheses are exhaustive. That means all possibilities are included in either the null hypothesis or in that of the alternative hypothesis. Therefore, these two hypotheses are said to be exhaustive because they can accommodate every possible hypothesis in either of these two alternatives. So, based on this definition, when you say null hypothesis, we are going to state something like pi equals 0.72. This represents something like a null hypothesis. And the same is true here, denoting mu equals 120 or mu equals 120 represents a null hypothesis because these two statements are saying that the population parameter and the assumed value are not different. The population parameter and the assumed value are not different. So these two hypotheses determines that these population parameters are not different from their corresponding assumed values. So these are the two mutually exclusive and exhaustive hypotheses in every statistical hypothesis testing. In general, in simple words, the null hypothesis states that there is no significant effect, no significant impact, no difference, no association, no correlation. On the other hand, the alternative hypothesis states that there is a significant effect, significant impact, significant difference, significant association, and significant correlation. So the null hypothesis always states that there is no impact or there is nothing at all. But the alternative states that there is an impact or there is a difference or there is something. In other words, the statement under H note is similar to the notion of innocence unless proven guilty. So now again let's assume theta be a parameter of interest and let theta not be it is assumed or hypothesized value. So the null hypothesis is going to be written as H naught theta equals theta naught. That means the population parameter and the assumed value have no difference. Then the alternative could be H1 theta is different from theta naught. This means the population parameter is different from the assumed value. Or it could be H1 theta greater than theta naught. The population parameter is greater than the assumed value. or it could be h1 theta less than theta naught. The population parameter is less than the assumed value. Therefore, always we write the null hypothesis as h naught theta equals theta naught, but the alternative could be either a different from type, greater than type, or less than type. Therefore, the statistical test has three different forms. One, it is called two-sided test. The null hypothesis is theta equals theta naught. The alternative, theta is different from theta naught. This is said to be two-sided test because when theta is different from theta naught, theta may be greater than theta naught or it could be less than theta naught. So this test is said to be two-sided test. In the case of the one-sided test, we could have a right-sided test or right-tailed test or left-sided test or left-tailed test. In the right-tailed test, here h naught will write always as theta equals theta naught. Then the alternative is theta is greater than theta naught. So here we are particularly interested whether the population parameter is greater than theta naught or not. So this is said to be right-tailed or right-sided test, and it is one-sided test. And on the left-tailed or left-sided test, the null hypothesis is going to be written in the same way as theta equals theta naught. And the alternative h1 should be written like theta is less than theta naught. And here we are particularly interested whether the population parameter theta is less than theta naught or not. So this is also a one-sided test. So in every statistical hypothesis testing, we could have these three options. One, a two-sided test, or a right-tailed test, or a left-tailed test. This is the way that we are going to denote the null and the alternative hypothesis for these three different types of options. Now let's consider errors in hypothesis testing. There are two main types of errors in hypothesis testing. One, it is called type 1 error, and the other type 2 error. The type 1 error is an error occurred if one rejects the null hypothesis which is actually true. Or in other words, rejecting a true null hypothesis is said to be type 1 error. The null hypothesis could be true, but if it is rejected, that means we are committing type 1 error. And the probability of making such type of error is said to be significance level. And it is usually denoted by the Greek letter alpha. This is the probability of rejecting a true null hypothesis or the probability of committing type 1 error. Now, if the probability of rejecting a true null hypothesis is alpha, then the probability of not rejecting a true null hypothesis is 1 minus alpha, and this is called confidence level. Alpha is the probability of rejecting a true null hypothesis. Then the probability of not rejecting a true null hypothesis is 1 minus alpha, which is called confidence level. So alpha is the probability of making type 1 error, probability of rejecting a true null hypothesis, and the confidence level is the probability of not rejecting a true null hypothesis, which is actually 1 minus alpha. And the second error is type 2 error. This error is an error that is going to be occurred if one fails to reject the null hypothesis, which is actually false. Or type 2 error is not rejecting a false null hypothesis. The null hypothesis could be false, but if it is not rejected, then we are committing type 2 error. And the probability of making type 2 error is usually denoted by this Greek letter beta. So if the probability of not rejecting a null hypothesis, which is actually false, is beta, then the probability of rejecting the null hypothesis, which is actually false, is 1 minus beta. And this 1 minus beta is called power of a test. So the null hypothesis may be false, If that is not rejecting, we are committing type 1 error. On the other hand, the null hypothesis may be false. If we reject, we are not committing type 1 error, and the probability of if the null hypothesis is false and if we reject it, that means we are not committing an error. And the probability of rejecting that null hypothesis, which is actually false, is power of a test. And it is just 1 minus the probability of committing type 2 error. So these are the two common types of errors in hypothesis testing. So let's consider this two considerations. One is the null hypothesis and the other our decision. Now, the null hypothesis may be actually true. If the null hypothesis is true, and if we do not reject this null hypothesis, then the decision is correct. But if the null hypothesis is true, and if we reject the null hypothesis, in that case, we are committing type 1 error. Rejecting H naught, where H naught is true. On the other hand, if the null hypothesis is false, if we do not reject it, then we are committing type 2 error. But if the null hypothesis is false, and if we reject H naught, then the decision is correct. Therefore, this is just rejecting the null hypothesis, which is actually false. And this one, it is just not rejecting the null hypothesis, which is actually true. Therefore, we have these two types of errors. Type 1 error, which is a rejection of a true null hypothesis, and type 2 error, which is failing to reject the null hypothesis, which is actually false, or not rejecting a false null hypothesis. So let's consider these two figures for a simple understanding of these type 1 and type 2 errors. Now, in the first figure here, the person is a man, and the second, the person is a woman. Now here the interest is to check whether the individual is pregnant or not. So here the null hypothesis states that there is no pregnancy, because the null hypothesis always states that there is nothing, no impact, no difference, no association, no correlation, and so on. So for these two pictures, the null hypothesis is no pregnancy, or the null hypothesis H naught states that there is no pregnancy. So for this individual, there is no pregnancy is true. But the doctor says you are pregnant. That means here H naught that states there is no pregnancy is true. But the doctor says you are pregnant. That means the doctor rejects the null hypothesis, which is actually true. Therefore, here we are committing type 1 error. On the other hand, here the null hypothesis again states there is no pregnancy. So for this woman, the null hypothesis may not be true. But the doctor says you are not pregnant. That means the doctor fails to reject the null hypothesis, which is actually false for this woman. So this error is called type 2 error. So the null hypothesis no pregnancy is rejected here, which is actually true. Type 1 error, no pregnancy is false for this woman. This false null hypothesis is not rejected. Therefore, it is type 2 error. Therefore, in the first, the probability of type 1 error, or the probability of rejecting a true null hypothesis, is nothing but probability of false positive. And the probability of type 2 error, or the probability of not rejecting a false null hypothesis, is the probability of false negative. So the probability of false positive is nothing but probability of rejecting H naught, which is actually true. rejecting H naught, which is actually true. That is alpha, probability of committing this type 1 error. For this picture or image, H naught status, there is no pregnancy. No pregnancy is true for this person, but the doctor rejects it. Therefore, he is committing type 1 error, or the probability of committing type 1 error here is alpha. Similarly, for the probability of type 2 error, which is the probability of false negative, we have the probability that H naught is not rejected, where H naught is actually false. So H naught states that there is no pregnancy. No pregnancy is false for this woman, but it is not rejected by the doctor. So here we are committing type 2 error, and the probability of committing this type 2 error is beta. So in statistical hypothesis testing, usually the aim is to minimize both type 1 and type 2 errors. But minimizing both simultaneously is not possible. So it is assumed that type 1 error is more severe compared to type 2 error. Therefore, first we need to fix this type 1 error and minimize type 2 error as much as possible. So we need to specify the maximum acceptable probability of rejecting a true null hypothesis, or the probability of committing type 1 error first. And the common choices for this significance level are 10%, 5%, and 1%. As said before, a significance level is nothing but the probability of rejecting a true null hypothesis, or the probability of committing type 1 error. So common probabilities of type 1 error are 10%, 5%, and 1%. Now, if the probability of committing type 1 error is 10%, then the probability of not committing type 1 error is called confidence level, and this confidence level is nothing but 1 minus 10%, that is 90%. Similarly, if the probability of committing type 1 error is 5%, and if we are interested, let's say, on the probability of not committing type 1 error, which is the confidence level, then this confidence level is 1 minus 5%, that is 95%. And the same is true. If the level of significance is 1%, then the confidence level is 99%. So the level of significance, or this significance level, is probability of committing type 1 error, or probability of rejecting a true null hypothesis. But confidence level is the probability of not rejecting a true null hypothesis, that is 1 minus alpha. So this significance level and confidence level are just complementary items, because the confidence level is 1 minus the significance level, or the significance level is 1 minus the confidence level. So usually we need to specify this level of significance in statistical hypothesis testing. So now let's see just the steps in hypothesis testing. In later videos, we'll consider the practical implementation of conducting hypothesis testing, but now let's see the procedures that we need to follow in conducting a statistical hypothesis testing. First, we need to state both the null and alternative hypothesis, that means H0 and H1. Second, we need to specify the maximum acceptable level of significance, or probability of committing type 1 error. Usually, the choices are 10%, 5%, and 1%. Then, once the level of significance is specified, next we have to obtain what we call the critical or tabulated value, T tabulated, from that of a theoretical probability distributions. Or we have to determine what we call the rejection or critical region of the null hypothesis. Now this T tabulated is going to be determined as T alpha for a one-sided test. Now T could be, let's say, a normal distribution, T distribution, or it could be any other distribution, like that of F distribution, chi-square, and so on. Specifically, for hypothesis with a two-sided alternatives, for a one-sided case, we need to specify as T alpha. But for a two-sided test, we are going to make T alpha over 2. Therefore, T alpha for a one-sided test or T alpha over 2 for a two-sided test are going to be obtained from a theoretical statistical distribution tables. Then once we obtain these values based on the specified level of significance, next we need to define a test statistic that is going to be calculated based on a sample data. And using that sample data, we need to determine its calculated value, which is called, let's say, T calculated. Now, T tabulated is going to be obtained from the theoretical statistical distribution tables, and this T calculated is going to be obtained using a certain sample data. Now, for making a decision whether to reject H nodes or not, we need to compare this, the tabulated value and the calculated value. Then there are two possible methods for making a decision about H nodes. One is called the critical value method, just comparing T tabulated from T calculated. If the absolute value of the calculated test statistic is greater than or equals to the tabulated value, in that case, H naught can be rejected. Otherwise, we do not reject H naught. And we have also another method which is called p-value method. Now we can consider alpha, alpha, it is considered as the actual, that's of the maximum acceptable probability of rejecting a true null hypothesis. So the p-value can be considered as the actual probability of rejecting a true null hypothesis. So the maximum is alpha, which is specified first. So if the actual probability of committing type 1 error is somewhat less than this maximum level, that means in that case we can reject H naught. Otherwise, we do not reject H naught. Then based on this decision, that is the rejection or not rejection of H naught, finally we are required to put a conclusion, or let's say final interpretation of the hypothesis testing results. So we will follow these 5 steps in conducting a statistical hypothesis testing. First, we need to state the null and alternative hypothesis. Next, we need to specify alpha. Based on alpha, we need to obtain the tabulated value of the test statistic from the theoretical statistical distribution tables. And this is actually T alpha for a one-sided test and T alpha over 2 for a two-sided test. Next, we need to compare these tabulated and calculated values of the test statistic to make a decision about H naught. So if the absolute value of the calculated test statistic is greater than or equals to that of the tabulated value, H naught can be rejected. And finally, we are going to have a conclusion. So let's see more about what a p-value means. A p-value is the probability of obtaining values of a test statistic as extreme as that observed if the null hypothesis is true. Or you can consider this p-value as the actual probability of committing type 1 error. So this p-value is obtained as the probability that the test statistic has a value greater than or equals to the absolute value of the calculated test statistic. This is for a one-sided test. And again, for a two-sided test, we need to multiply by 2. Just the 2 times the probability of t greater than or equals to the absolute values of the calculated test statistic. So if this p-value is less than the maximum acceptable level of significance, H naught can be rejected. So now let's define what is a significant test. What do you mean by a test is significant? Now, if the null hypothesis H naught is rejected, then the test is said to be statistically significant. So a statistically significant test is nothing but a test where H naught is rejected. But if H naught is not rejected, the test is said to be insignificant, or the test is not significant. So the final interpretations, the null hypothesis H naught is rejected. That means when there is sufficient evidence against it. Once we reject H naught, or let's say if the test is significant, that means there is sufficient evidence against H naught. And once the test is significant, or once H naught is rejected, we have to answer some questions. For example, we need to identify the direction of the effect. In comparing two or more groups, we are interested to identify which group performed better, or which group has higher value. In studying associations or correlations, we are interested in identifying whether the relationship is positive or negative. And second, once H naught is rejected, or once the test is significant, we are interested also on the size of the effect. Therefore, we are interested in determining the effect size, confidence intervals, or both. And the other one thing that we are going to note is that a statistically significant test doesn't indicate practical or clinical importance or significance. So statistical significance and clinical importance are different. In the test that we are going to conduct, the test may be significant, but that significant test may not necessarily imply clinical importance or clinical significance. So to determine whether the statistical importance is actually clinically important, there should be a certain judgment whether the result has a practical or clinical importance or significance based on a certain subject matter experts. But in general, statistical significance is not necessarily an indication of a clinical significance or clinical importance. So this is all about today's video. We'll consider practical examples in the next coming videos. Thank you.